Right. One is due dates for stuff. There's some questions to whether or not there is anything, we're covering material, is there anything due related to it? That was one question. Answer to that question is no, not really. This is a term project, so it's up to you when you want to get stuff done. In order to kind of provide some structure, I edited the deliverables on the assignment document, which is updated on Canvas. Essentially, it puts all the weather and rotor modeling stuff due at the last Friday before spring break, so the 28th. You don't have to do any of the cost modeling or optimization or stuff like that. Essentially, you have to do what we did last class for every month for 5 years of data, then create a rotor model, which we're going to go over in this class.
Are we supposed to just do 1 year? Or is it everybody's doing 5 years?
Yeah, so that's thing two. I was thinking about how I was about how I had the group work divvied up, and it just wasn't really making sense. And so it's just gonna be everyone does their own project.
Okay.
Yeah. So that should take care of that. Any questions on there? Great. Okay, so that's that. And there's a list of the 3 items that I'm really looking for at the term on that document. So that's that. Thing 2. Oh gosh, if I can remember thing 2, it'd be wonderful. Oh yeah. Why wind stuff? So we've been covering a lot of wind energy stuff. This is an energy conversion class, so you guys are going to talk about other non-mechanical means of energy generation as well as other mechanical means of energy generations like steam, nuclear, whatever. Solar, I think, makes an appearance out of hand. Why wind for the project? To be honest, it's somewhat arbitrary. You're going over a fairly diverse spectrum of energy conversion means. So I picked wind, one, because I knew enough about it to make a project. 2, the idea is to show an interplay between an energy conversion method and real world constraints. And wind you can kind of get at that pretty quickly from not too much. And we're trying to front load that information so that you can just go ahead and schedule the project kind of at your own pace. You don't have to wait that long for stuff to occur. So to be fair, it is a bit of an arbitrary choice, but it contains a lot of the nuances of energy conversion and use that the class is kind of looking to probe, so it works. Okay, so I think that's all the question stuff. In terms of all the Monte Carlo stuff that we went through last class, I think we're all set on that. I'll touch on it a little bit at the end of this. But from the outset, I want to focus on 2 things. One is we've talked about the atmosphere from the perspective of buoy data. Now we're going to talk about it from the perspective of wind speed at hub height, at whatever the turbine rotor, at whatever the turbine's height is. So we need to project wind speed up into there. The next thing we need to do is be able to model the power generated by a rotor. So we'll start off with the atmosphere. This is something called the atmospheric boundary layer. This is a description of it. As I think I mentioned at one point, the kind of the defining characteristic of air, or how do I say, of air flowing over ground isn't necessarily its speed; it's how that speed changes with altitude. air is a viscous substance. It's not very viscous. If you think of water or honey, that's actually a viscous fluid, meaning that has viscosity that you care about. Although on a day-to-day basis, we kind of move through the air and it doesn't really matter. Meanwhile, people are sitting with exercise programs and walking through pools, right? However, air has viscosity. It is inherently sticky. That's why airplanes work, because air will conform to the shape of the wing geometry. And the same way, because air is sticky, because it is affected by other fluids or other solids that it interfaces with, its velocity is going to change as it moves away from the ground. If we go down right to the point where the air meets the ground. I'm going to try to use this pointer on screen, but the screen's not exactly the best. If we look at that point right at the ground, where there's an air molecule sitting on the dirt, it's actually not going to be moving because of its viscosity. And that's called a no-slip condition. The further you move away from the ground, the less that air molecule is being affected by the fact that there's a solid there, by the fact that there's a ground there. The ground there. You might think of this as if I have how am I going to say this? If I really close to this wall, there's some water between myself and the wall. It's relatively easy for me to feel that there's a wall hole there because of how it's going to interact with water. Maybe a better explanation would be if there are two people swimming, if you can feel the other person swimming if they're relatively close because of the currents that they're making. The further you are away from them, the less you're going to feel the waves that they're creating. The viscous interactions are far less. So the higher you go in the atmospheric boundary layer, generally speaking, the less his viscous interactions you'll have with the ground, so the faster the air will be able to move. This gets more complicated if you throw in buildings or factories, trees, hills, surface features, all that kind of stuff, which is kind of the issue with onshore wind turbines. That's why we have turbines up on the Allegheny Ridge here, because the air is moving faster. But it's also the reason why you don't really see a lot of wind turbines in Pennsylvania. There are a lot of rolling hills. It's called and they're all at. How do I say this? And the only really flat areas that you can put a wind turbine are low and usually near cities, because that's the only flat area around. So you're not going to get a lot of high quality, high speed flow around here. Now go out to Texas, say, and you have all kinds of flat land. Outside, actually, I think including California, Texas is the largest producer of wind energy in the U.S. right now, because they have so much flat land that they can use for it. Area that doesn't have obstructions. There's also the motivation for going offshore, because there aren't any obstructions. It's just flat water. So the average wind speed is higher at a given altitude. Now, for us, we have taken up a bunch of buoy data. We've gone over to the National Buoy Data Center. And we have a bunch of data from a buoy sitting out offshore of Atlantic City. So I think that it's collected from a height of 5 meters. We need to somehow parlay that into the wind speed 75 meters above it. We've established our hub height as 80 meters, and for purposes of resource assessment and power estimation, we are going to use the hub height wind speed as the wind speed that the entire rotor sees. So you don't need to feel like you have to model wind speed as it changes across the rotor disk itself. We're just going to estimate the hub height wind speed and go from there. So next question is, okay, so if we want the hub height wind speed, how do we do it? We got two options. Ooh, I think went away. That's unfortunate. Okay. My notes vanished. Let's grab that quick. So there are two methods for doing this. Essentially, two ways of assuming assuming a profile to the atmospheric boundary layer. One's called the log law. We're going to use the power law. So what this power law says is that there have been a number of experimental measurement campaigns, and they've determined that while the actual speed in the atmospheric boundary layer, as you go up in altitude from 0, while the actual speed is somewhat chaotic, there's a fair amount of turbulence, especially in the lower atmosphere. If you plot a mean value through that, you think of that as like a wind speed measurement. If you plot a mean value through that, it follows an exponential curve. So you can express it as the wind speed at some height z. So say this is some height z above the ground, and that's the wind speed at that altitude. That's going to increase at an exponential rate when compared to some reference speed. So in our case, that reference is our buoy data, which is taken from a height, you might call it Z ref, of 5 meters. So the rate that it varies is proportional to the altitude that you're looking at over that reference height to some power alpha. So the real question is, okay, that's cool. What the crap is alpha, right? So short answer is that it depends. It depends on a couple of things. There have been a few experimental studies to determine a good coefficient for alpha, quote unquote. One is considered a trendline fitting of velocity as a function of height, based on that reference. There's another one that we're going to use that expresses alpha as a function of surface roughness. So you can think of surface roughness as how big obstacles on the ground are. Because if I have a skyscraper and wind's blowing over that, it's going to create more turbulence. It's going to increase the it's going to delay the natural increase of wind speed as you go up through the atmospheric boundary layer. Essentially, the flatter and less rough the surfaces, the better. So if we can model that exponent as kind of a function of how big obstacles are on the ground, that'd be like a useful thing. So, so the expression for alpha is again a correlation that is something like this. Log base 10 of some surface roughness factor, that's z naught. Plus 0.016 base 10 naught squared plus 0.23. So that's a correlation based on surface roughness. Note those are all log base 10s in there, and it spits out alpha. Of course, next question is, okay, well, this just muddied the waters a little bit more, right? We said, okay, we need to know alpha, now we need to know what the surface roughness factor is. So conveniently, we have a table of those. If the next question is, are they available online? They will be soon. It looks something like that. So based on what the terrain is, your surface roughness factor Z naught changes based on that. So we are on a calm open sea, so Z naught that we'll use will be 0.2. So if we plug that puppy into this expression, it should pop out an alpha in the vicinity. I have to review the math to check it, but it should pop out an alpha that's close to 1/7. I'll leave the actual computation up to you. And that's that. Essentially, we can just stick in our buoy data for ref, for the new ref, 5 meters for Z ref, desired altitude for Z, whatever comes out of this expression for alpha, there we go. And it'll spit out a hub height wind speed for us. So we can do that for all the buoy data that we have, and we'll get a prediction of wind speed at hub height. Cool beans? Sweet. All right, so now that we know how fast air is moving at hub height, next question is, great, how do we get power? So, ask no more. So we're going to model our turbine. And rather, we're going to model our rotor. We're going to model it from first principles, because we don't really know what the rotor looks like. We don't know what the blade is like. We don't know we barely know what the thing's made out of. We don't know what the airfoils are, how it's twisted, tapered, whatever. We don't know any of that. And we shouldn't know any of that. We're so far into the conceptual whole phases of this thing that really the rotors just exist as things which call as conceptual artifacts. So one way to approach modeling them is using something called momentum theory. which is what we're about to go into. So in this, the rotor is modeled as a disc with some dimensions to it. So essentially the rotor diameter. So we have this disc so we have this disc here. Again, it has no properties other than it has a size, a physical size, and induces a momentum change. That's it. That's all. Oh yeah, and energy is extracted along that disk. That is it. That is all that we know about it. A couple other things that we need to keep in mind. In order to take a few of the other variables out of this analysis and simplify it to the point where we can do something, we're going to assume a few things. One is that we have quasi 1D flow, meaning that we're going to assume that the flow is all moving in one dimension. There's no cross flow, nothing going up and down. It's just going through the rotors. So whatever the hub height wind speed that we computed, it's going through that rotor directly. There's no up, down, left, right. It's just going straight through the rotor. Thing two, flow is inviscid, which might seem weird given that we just got through all this talk about air being a viscous substance. Now we're going to say it's inviscid, being a non-viscous substance. What that assumption more or less states is that there are no significant viscous interactions between the air and the rotor itself. These sort of things usually come out as losses. It's a loss of energy from the air that doesn't do us any good. You can think of it as friction. So we're going to neglect inviscid losses right now, in part because in order to quantify the inviscid losses, we'd have to actually know the geometry of the rotor itself. We can do a little bit of a fudge factor for now, but that's kind of it. We're also going to assume that the flow is incompressible. This is actually probably the most realistic of our assumptions, outside of the quasi 1D is mostly true. Incompressible is definitely the most sensible of our assumptions. What this is saying is that the density of air does not change significantly throughout its entire movement through the control volume that we've outlined here. So, so the question is this a reasonable assumption? For that, you have to define where it's valid. And Coy doesn't have to listen because he's heard this for like a week and a half now. So, for a fluid to be incompressible, if its density, for something to be incompressible, there we go, incompressible, its density has to change by less than 5% of its mean value. So what causes it to change? So say that I have a turbine blade. I'll draw a cross section of a turbine blade here. We have flow moving in at it. When the flow gets to the blade, it's going to turn around it and try to follow the geometry of the blade itself. And that's going to create lift and torque and cruise power and blah, 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 blah. Now, the question is, how does the air, quote unquote, know to turn around the blade? Because it starts turning, if I keep drawing these streamlines, it turns even for the stuff that's further away from the blade. And the answer is pressure. This is how wings work. Because there's something in the flow can form to that shape because it's a viscous fluid. I know I said that we're assuming it's inviscid. We're just assuming it's inviscid in terms of its effects. We're still assuming that it does all the usual turbine blade stuff. All of it still flows as it should flow. So as the fluid turns around a solid body in the flow, its pressure is going to change. You might think of it as, like for this streamline here, it's turning away from itself. So you might think of it as creating an expansion zone. So expanding air, lower pressure, right? And that low pressure zone, if I kind of drew like a contour of pressure, it pulls the rest of the air in that direction as well. Information, you might say, is transmitted through a fluid via pressure. Now, pressure waves, well, you think of them like sound waves. Sound waves are pressure waves, so just very, very small amounts of pressure going through a fluid, propagating through a fluid. If I have fluid that starts to move close to the speed of sound, say, close to Mach 1, which again is much faster than we're talking about for wind turbines. If I have a fluid that's moving close to the speed of sound, then it's moving at least as fast as those pressure waves are propagating through the fluid. So if I have a pressure wave here that's trying to go upstream and would tell, quote unquote, the fluid to turn, to move around the body that is about to encounter, this air is moving downstream faster than those sound waves are moving, than those pressure waves are moving upstream. As a result, for flow near the speed of sound or above the speed of sound, you have a bunch of air getting very, very close to the airflow before it has to move. Nature's way of resolving this problem is a shock wave, which creates almost instantaneous velocity change as well as significant pressure and temperature changes. Blah 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 blah. Because of that, you essentially get a bunch of air compressing behind the shock wave. You have these huge density gradients. This is very compressible flow. For a Mach number, it's approaching the speed of sound. However, as you might imagine, that's an extreme case. We're kind of on a continuum here. The density changes as you approach. Density changes in a flow increase as you approach Mach 1. So generally, the rule of thumb is that for a Mach number less than 0.3, you can assume that your flow is incompressible. For every flow velocity that we'll see, we're going to satisfy that criteria. For reference, speed of sound is about 340 meters per second. So that means that Mach 0.3 is what, 102 meters per second, and the cutout speed of our turbines is 25. So we are very much in the incompressible region. Thank you for allowing me to nerd out there a little bit about fluid dynamics. So that's actually a pretty reasonable. So the incompressible bit's actually a pretty reasonable assumption. Last one is irrotational flow. This was the one that we might get into a little bit of trouble with, but we're still going to have a decent model even assuming it. The reason why I say it's a little troublesome is because we have a turbine with these long spinning blades that are moving slowly. The flow is actually going to be dominated by inertial forces at this point. So the fact that we have spinning blades in a viscous fluid, talking about the real effects of having a turbine, means that they're going to impart some swirl into the flow. And the flow is going to be rotational, and that's going to consume a little bit of the energy that we otherwise would account as being extracted by the turbine. So we're going to assume irrotational, and as said with the viscid effects, sorry, the viscous effects that we're also neglecting, we're going to add in a fudge factor to account for that. So there we go. There you have it. Those are our assumptions. Insofar as the rest of this puppy goes, for the quasi 1D, the assumption we're assuming that flow is only moving in through this boundary, only going out through this boundary. These red lines on the side, these streamlines on the side, denote some arbitrary line through which no fluid passes. As a rule of thumb, the amount of air captured by a rotor comes from a significantly larger area than the area of the rotor disc itself, and then it shrinks down as it goes through the disc. So that's kind of what our control volume looks like. All right. So in order to model this, we're going to first just look at our conservation loss. Actually, we are going to look at our conservation loss. We'll start with conservation of mass. So if I have some fluid, and it's going to start here, say, there's some, let's call it, I'm looking at some cross-sectional area of fluid. It's moving at some speed v, and we're going to say it's going to move for some time dt. Question is, can I get an expression for mass out of that so I can come up with an expression for the conservation of mass? So let's see what we can do about this. So I'm going to try to reproduce it here because my stylus is not doing too hot today. There we go. So got some cross-sectional area there. Moving at some velocity for some length of time dt. Question is, first, can I use this information to get mass? And I know that the fluid has some density, rho, and I kind of know what that density is. At sea level under standard conditions, it's 1.225 kilograms per meter cubed, or for whatever reason you like English units, it's like 2237 slugs per cubic foot. You have to double check on that though. Anyhow, so I know density, and density is just a mass per unit volume. So if I can figure out volume, I can get mass. Sweet. So if I know my cross-sectional area, if I draw this into, say, 3D, it might make it look a little bit better. If I know my cross-sectional area here, and I know how far it's, and I have some speed, and I have some length of time, that's kind of like a volume, right? Because like speed is distance over time, speed times some time is a distance, that gives me kind of my depth, times an area gives me a volume, right? So I can say that mass equals density times area times some velocity and I've allowed the flow to move for some time dt, for some small unit time dt. But however, this gives me an expression for mass. We usually think of conservation of mass in terms of like mass flow rates, in terms of mass entering and leaving a domain. So I need to find the time derivative of this. So take the time derivative of that. So dm dt, the time rate of change of mass in a given control volume, also abbreviated as m dot, the dot being the time derivative, is equal to rho av or rho va, depending on how you decide to memorize it, or the velocity that a cross-section of fluid is moving at multiplied by its density. Cool. Now, if I have some control volume, like I do, I have some m dot in, I have some m dot out, and this is steady flow. If I don't have, if I'm not adding any mass, I'm not subtracting any mass from that control volume, how are m dot in and m dot out related? Yeah. If I'm not taking anything out, I'm not putting anything in, what goes in has to equal what comes out. So that's our expression for the conservation of mass. M dot in is m dot out. If I had a cross-section area for up here and down here, a velocity for up here, which I have, that's whatever the transformation of the wind velocity for my buoy data gets me. And if I had a velocity for out there, I could compute what each one of those are, and they'd be the same. Conversely, it also means that if I look at my rotor, well, I know its area, don't quite know its velocity, but if I can find that out, m dot here should be m dot here, should be m dot here, should be m dot here. M dot should be the same everywhere along any cross section in that domain. So if I can figure out one of those, I can figure out all of them. That's going to come with us. So that's conservation of mass. Next thing, conservation of momentum. So y'all know Newton's second law, F equals ma. I'm going to tell you that you've been lied to for years. It's actually not F equals ma. It's force equals the time rate of change of momentum. Ooh, there we go. Focus, camera. Even the camera was surprised. So this is a big deal because it means that we're not just limited to taking the time derivative of acceleration and for a constant mass. We can take the time derivative of mass for a constant velocity. And in this case, that actually works out well for us because, well, we happen to have an expression for the time derivative of mass. So we can say that the summation of forces is the summation of these time rates of change of momentum instead. So let's give this a shot for our rotor. So we got this. It'd be cool to find out the thrust generated by the rotor. Maybe that would help us start relate these different properties together. And we know from physics that for a constant force and a velocity in the same direction, we can figure out power. Maybe there's some relation there that we can. What am I trying to say? That we can leverage. So let's look at doing a momentum balance across the inlet and the outlet of the rotor. So U1 and U4. So the change in momentum between the inlet and the outlet, that difference would be produced by this rotor. So, game on. So if I was to do that, say that the rotor thrust, T, would be equal to, let's do a quick sketch of our control volume here. So I've got U4 at the back end, U1 at the front end, rotor's in the middle, and there's m dot here, and they're the same. So, oh, I'm sorry, thank you. Actually, I'll just zoom out a little. So I have some momentum entering, some momentum leaving. The sign convention is that, so the sign convention that I'm going to use rather is that things entering the control volume have a positive sign, things leaving have a negative sign. So m dot u1 is some momentum entering the control volume, and then I have some momentum that's leaving the control volume. So I can get an expression for momentum balance across the whole thing like that. We're still hurting for actual something that we can use, right? Because, well, this is great, but I still don't know U4. I don't know all the components of M dot. I'm still a little stuck. Okay, so let's see what other equations that we can pull out. That we can pull out of the back here. Oh, before I forget, if you're looking at this and going, wait a second, what about pressure on all sides of this thing? Because we're going to assume that the inlet and outlet are sufficiently far away from the rotor that P1 and P4, or the static pressure at the inlet and the outlet, are the same as the ambient pressure at that particular location, or roughly one atmosphere. We also said that there's no flow going through the sides, so that means that pressure here and pressure here are equal to one another, both top and bottom. So there are no pressure forces. We're just looking at momentum. The only thing that causes a change in momentum here, or exerts a force on the control volume, is this kind of momentum exchange of fluid going into and out of the control volume, as well as whatever the rotor is doing. Okay, so next, what's called the next thing, which will be the last thing for today, is this is conservation of momentum. And that still hasn't given us all the answers. Well, our last tool is conservation of energy. So, game on. So if I have my rotor, here's my stream to begin. 1, 4. Great. There's some other things in there. 3, 1, 4. There's the ambient. Okay, so the last tool that I have in my bag of tricks is conservation of energy. One expression of the conservation of energy is Bernoulli's equation. So you might remember pressure, not pressure equals pressure plus 1/2 ρB squared constant. You've probably seen that before at least once in once in your fluid mechanics lives. So this is true, but so the trick is that this is an expression of conservation of energy energy.
Is that a plus or a multiplier?
That is a plus. I'm
Right. I just want to make sure.
Yep. The trick is that this rotor is extracting energy. That's like the reason why it's there. So this statement of conservation of energy is not true across the rotor disc. It's valid here, and it's valid here, but it's not valid if I try to connect that's what's called one side to the other. Her energy is not conserved across the disc because it's being extracted from the fluid. You might say it's not the amount of energy in the air is not being conserved. Overall, the laws of thermodynamics still apply. If we did, we'd have problems. So I can apply conservation of energy from state 1 to state 2, kind of the inlet to one face of the rotor disk. I can apply the conservation of energy from the back end of the rotor disk to the outlet, and that's kind of it. So, but because we can relate the inlet and the outlet via pressure, maybe we can start coming up with expressions for things. So, let's start with the front end. So, let's say P1 plus 1/2 rho U1 squared equals pressure at 2 plus 1/2 rho U2 squared. That's true, and I can do the same thing for the back end. P3 plus 1/2 rho U3 squared equals P4 plus 1/2 rho U3. There we go. U3 squared. I can do that. We're going to make another assumption in here, and that's that U2 is approximately U3. Again, it's moving across a rotor disk. We're focusing on energy extraction for the volume of air moving through. It's not going to change the kinetic energy of the air too much in the long run. So we're going to assume that UT and U3 are relatively small. There might be a little white lie, but we'll see. Now, you mentioned, yes, we can use this to relate maybe U4 to some parameters that we know, like the ambient pressure, like U1, which is our free stream speed. That's from our transformed buoy data. But we can also think of maybe this is another way to approach getting rotor thrust. The momentum balance isn't the only game in town. I can also say, well, if I have pressure on this side of the rotor and I have pressure on this side of the rotor, well, then the pressure difference is my thrust, yeah? So another way of expressing that would be like thrust equals some the cross-sectional area of the rotor times that pressure difference. We're going to say that this is our positive direction. The downstream is positive, so T equals A times P2 minus P3. So if we have that, I can take these expressions. I can kind of jam them. Together and solve for this factor directly. So could solve for P2 in the first expression and get something like P2 equals P1 plus 1/2 rho U1 squared minus U2 squared. I can solve for P3 in the second one, same deal. P4 plus 1/2 rho U3 squared minus U4. Sorry, I wrote that as a 3 before it should be a 4. Cool. And then I can just say, okay, P2 minus P3, take these two expressions, subtract them from one another, remembering that U2 is approximately U3, and that P1 and P4 are equal to one another, and out of that pops something that looks like this. Sweet. So we're getting we're getting closer all the closer all the time. Sweet. Now we take that. Sorry, I'll leave that there for a second. So if we take that and yeah, grab this guy from over here. There we go. We take that expression together with the, there we go, the other expression for thrust that we came up with both before. These are both expressions of thrust, so we can equate them to one another. If we do that and substitute in value for m dot, say rho u2a, that'd be mass flow rate at the rotor disk. We can, we start getting some expressions, instance, for these different factors. Excuse me. One thing that one kind of interesting result of doing this is that as a result of all this modeling, once we kind of set those two equals, solve that down, which I'm not going to do here because we're running out of time. You end up with the velocity at the rotor plane actually being the average of the inlet and the outlet velocities. The other thing that we come out with is this notion that, well, this is all well and good, but we don't know what this outlet velocity is. We can't find it. We need to approximate the velocity at the rotor plane somehow. We know that the velocity is going to change by some amount. We just don't know by how much. So, welcome to the world of the bets limit, which kind of defines which is a factor that estimates the velocity change from the inlet to the rotor plane, and is something that we'll talk about next time. Any questions for this week? Cool. In that case, thanks for stopping by.